So let's understand before framing or coming to quantum mechanics, first of all, why a particle needs to be a vector.
When we say a particle is represented as a vector, it's because quantum mechanics is fundamentally linear. The state of a particle is described in a mathematical structure called a Hilbert space. Vectors in this space encode everything about the state, like the probability of finding the particle in a particular position or energy. Since vectors can be added together or scaled, this allows for superposition, a key quantum feature where multiple states combine into new possibilities. In short, the vector form gives us the tools to describe, predict, and manipulate quantum outcomes.
So before that, can you explain why was that? Uh, it must be a experimental evidence. Then they wrote down mathematically so that the vector may be the state represented as a vector.
Yes, the mathematics evolved to explain what experiments showed. Early on, experiments like the double slit or the Stern-Gerlach experiment revealed that particles don't behave like little billiard balls. Instead, they produced interference patterns or quantized outcomes. To explain these strange results, physicists like Heisenberg and Schrödinger developed a formalism. They realized a particle's state needed to capture probabilities and how states evolve. Vectors in a complex space fit perfectly. They let you model superposition and predict probabilities. So, yes, experiments showed weirdness, and the vector formalism was the elegant mathematical solution.
So state needed to capture the probabilities and how state evolves. So vector capture that picture perfectly. And what about
If you're wondering what about the probabilities in evolution, well, that's where the magic of vectors shines. The length squared of a vector component gives you the probability of measuring a particular outcome. This is the famous Born rule. And evolution? The Schrödinger equation governs how these vectors change with time. In other words, vectors capture both the instant snapshot of probabilities and the dynamic unfolding of the quantum world.
so basically a vector is the essence where the state is being captured for a quantum world. But in general mathematics, when we talk about vector, did we specify that the state? No. Before that, the vector at this vector quantity will work at that scale in the quantum world.
In general mathematics, vectors emerged long before quantum mechanics. They were simply tools to represent things like forces, velocities, or displacements, geometric objects with magnitude and direction. No inherent connection to states or probability was assumed. But once physicists saw that quantum states needed a structure that allowed superposition and complex amplitudes, the vector concept was adapted. In quantum mechanics, vectors live in Hilbert spaces, and those spaces come with inner products, allowing us to define probabilities. So while vectors weren't invented for quantum mechanics, they were a perfect fit when quantum states needed a home.
But you didn't answer the question that, like, I need to know that this quantum world is very small scale working.
Ah, I see what you're driving at. In classical physics, vectors represented macroscopic things, like forces or directions. But when we zoomed down to the quantum scale, atoms, electrons, photons, we needed a framework that captured probabilities and superpositions. The quantum world didn't force vectors. It showed us that at this scale, states had to be represented by something allowing interference and probabilities. Vectors, now in complex Hilbert spaces, just happened to be the right mathematical tool. So it wasn't predetermined. Experiments showed the quantum scale needed this richer structure.
So, what about the rotation and the angle thing? How did that?
Rotations and angles naturally arose from classical geometry. When vectors were used for real world things, like forces, rotations were simply changes in direction. But when we moved to quantum mechanics, these same mathematical ideas became more abstract. In quantum systems, rotations correspond to changing the basis in which you describe the state. The angles are tied to phase changes or transformations in the state space. So that familiar geometric concept was repurposed. In essence, quantum rotations don't move particles in space. They rotate the perspective in the abstract space of states.
Okay, can you make a conclusion from what we discussed?
Sure, we started with why quantum states are represented by vectors. Initially, vectors were just tools for classical directions and forces. But as experiments revealed the quantum world, where probabilities, superpositions, and interference dominated, vectors became the natural mathematical language. They let us encode quantum states, measure probabilities, and evolve states in time. Rotations and angles, which were geometric at first, became abstract transformations of state spaces. In short, the quantum world took familiar math and gave it deeper meaning. Vectors now hold the essence of what a quantum state is.
Okay, thank you.